We're continuing on here in the gas chapter. And obviously, we started talking about gases and we talked about some units of gases, which again, the three main units that we most often come across are atmospheres. And one atmosphere is equal to 760 millimeters of mercury, and that equals 760 torr. There definitely is other units of pressure like kilopascals, pascals, psi, bar, but I would say again, these are going to be your kind of big three in terms of units. We talked about sort of some gas laws and relationships. We talked about Boyle's law, and Boyle's law is P1 V1 equals P2 V2. Remember that this is at constant temperature. And the relationship that we saw with Boyle's law is basically as the pressure goes up, we see a decrease in the volume, and vice versa, pressure goes down as the volume goes up. Again, as the volume goes down or gets smaller, we have a lot more collisions occurring and causing a lot more pressure that's going to occur. And vice versa, as the volume gets larger, we will have less collisions and less pressure. I think we finished up talking last time about a couple gas laws. Charles' law, V1 T1 equals V2 T2. And this is Charles. And this is at constant pressure. And what we saw in terms of this relationship is as the temperature increases, so does the volume. And as the temperature goes down, so does the volume. And again, it is here, as we talked about, it is the volume that adjusts that allows the pressure to remain constant. So when we do increase the temperature, even though the gas molecules are flying around faster, what happens is the volume adjusts larger, and even though they're moving faster, there's still basically the same number of collisions, and that's what's able to basically keep the pressure constant. Vice versa as well, as we lower the temperature, everybody's going to be flying around slower, so we kind of squish everybody together, and what that does, again, even though they're flying around slower, they have a shorter distance to go to cause collisions, and we see that the pressure will remain constant. Now, in terms of Boyle's law, the units really don't matter for either pressure or volume. They could be any units you want, as long as they are the same on both sides, obviously, of the equal sign. Now, in terms of Charles' law here, our temperature definitely needs to be in Kelvin. And as we talked about, that's sort of the relationship that we saw, that if you could take any gas you like, and if you graph volume versus temperature, they will all hit the same spot, which is that absolute zero, minus 273.15 degrees Celsius. So basically, again, it should be a no-brainer. If you're doing any type of gas law and its temperature, that should probably be the exact first thing you do, is just convert it into Kelvin. Again, as I talked about last time, even if the problem gives it to you in Celsius, wants the answer in Celsius, you do need to put it into Kelvin and go into the gas law before you kind of do the last conversion. Volume here can be any unit you like, again, as long as they're the same. We saw Gay-Lussac's law, and that was something like P1 T1 equals P2 T2. And I think we talked about this relationship here. This is at constant volume, this particular relationship. So different here is actually the volume is locked into place. So it will not adjust as the temperature adjusts. So as the temperature goes up, because the volume stays put, unlike in Charles' law, we definitely will see an increase in pressure, because basically they're going to be flying around faster, the volume's the same, they're going to have a lot more collisions occurring, and that's going to increase pressure. Vice versa here, we lower the temperature, going to fly around slower, going to cause less collisions, and we will see the pressure come down. Once again here, temperature in Kelvin on both sides. Pressures can be any unit you want on both sides, as long, again, they are the same. Any questions on those? I think that's where we laid up, if I'm mistaken there. All right, then I think we didn't do this example, so why don't we do this example, I think. A sample of carbon monoxide gas occupies 3.2 liters at 125 degrees. At what temperature will it occupy 1.54 liters? So take a moment there, see what you come up with. So let's take a look. So remember, as I talked about before, a lot of times it's a good idea just to pull out the information from the problem, kind of label what it is. So obviously here we have volume as 3.2 liters. We have a temperature that's 125 degrees Celsius. We are looking for another temperature, and we have another volume at 1.54 liters. So we have a few to choose from at this point. Clearly, there's no pressure, so that eliminates these two. So again, you can kind of see Charles' law there as you just kind of do it. We can label the first set of information ones and twos. Once again, it really doesn't matter as long as you do keep the information that goes together. Like normal here, our volume is liters on both sides, so we're good to go. Like normal, though, we do need to do our conversion here to Kelvin. Again, almost should be kind of like the first thing that you do. 125 plus a 273. We'll go with 398 in this case, Kelvin. We're going to go V1 T1 equals V2 T2. We're actually going to solve for T2, which means we're going to take it to the other side. It's going to go in the opposite location up on top. We also need to move these guys to the opposite locations. And if you rearrange that correctly, you will get T2 is equal to V2 T1 V1. Basically, we're multiplying T2 to both sides, dividing by V1 to both sides, and multiplying T1 there to both sides. And that is what we should end up with right there, as those cancel and those cancel. Yeah. All right, so we want to make sure we put our numbers in correctly. So V2 going up on top, 1.54 liters. T1, which is in Kelvin, and our V1, which is 3.2 liters. Liters will cancel. We will be left with Kelvin up on top, which is good since we're looking for a temperature here. And that's going to be a 1.54 times a 398 divided by a 3.20. It's going to be about 190, I will call it 2 degrees Celsius, not degrees Celsius. Actually, it's Kelvin here in this case. If I did want degrees Celsius, I could subtract 273 from that, and that would get me in the ballpark of 81.5 degrees Celsius, right? Didn't really specify, so you could give the answer in any unit you want in this case. Once again here, if we look at our relationship, the volume went down in this case. And because this is Charles' law, we should also expect the temperature to go down. And that's what we see. It went from 125 downwards to negative, by the way. 81.5 would be good to throw that negative in there, I suppose. It definitely went much lower. Or if you compare the kelvins, it went from 398 to 192. Any questions on that one there? All right, let's try a couple more here. In the experiment, we have 452 milliliters of a light bulb heated from 22 to 187. What is the final? Okay, so once again here, if we kind of pull out the information, we have a volume that's 452 milliliters. We have a temperature that's 22 degrees Celsius. We have another temperature that's 187, and we are looking for a volume in this case. Again, just looking at the information in the problem, it should really point you in the direction of Charles' law, as obviously we have volumes and temperatures given to us. I can call the first set here ones, these guys two. Going to add like our kind of normal calculation here, going to convert our temperature here into Kelvin. So got a 22 plus a 273. Going to do a 295 Kelvin and a 187 plus a 273, 460, it looks like. Here we are solving for V2, which means we basically just need to move this guy to the opposite location up on top. And that will put me at V1 T2 over T1 equals my V2. Again, making sure that we do put the numbers in the correct locations. We got 452 milliliters up on top. It is going to be T2 up on top. And our T1 will be on the bottom. Here, our kelvins will cancel. That means that our volume in this case will be in milliliters, as that's the only unit left. 452 times a 460 divided by a 295 and give us about a 705 milliliters in this case. Once again here, this is a Charles law relationship. So when we look at the temperature went up. So we would expect the volume to also go up. So it went from 452 to 705. So it did go up in sort of the right way. And that's sometimes a good thing to kind of look at just in case, it's very common in gas laws that people will kind of inverse numbers, maybe do a T1 for a T2 or that type of thing. So, you could at least check to make sure it is moving sort of in the correct direction based on the relationship. Any questions on that calculation? Yeah. Yeah, it's always the temperature in any gas law. That again should be pretty much the first thing you do is put it into Kelvin. They're pretty much every single gas law formula that you use, the temperature when it goes into it needs to be in Kelvin. And again, sometimes, like I said, people will come across problems, very common in books. Like I said, they would kind of give you the temperature in Celsius. They didn't even ask you for the answer in Celsius. And that sometimes tricks people in their head going, I don't really need to convert it or not, but you always 100% gas law, temperature should be Kelvin. Now, other questions? Now, in this case, the volume really doesn't matter as long as, again, they are the same on both sides. So the units cancel out correctly. Other questions on that? Let's try another one here. We got argon in another light bulb. And it contains 1.20 atmospheres at 18 degrees Celsius. We heat it up to 85 degrees. What is the final pressure of this light bulb? Okay, so taking a look at this one, again, pulling the information out, we have a pressure at 1.2 atmospheres. The corresponding temperature for that one there is 18 degrees Celsius. We have another temperature of 85 degrees Celsius. And again, we are looking for a pressure. So this eliminates Boyle's law as there's no volumes mentioned. Also eliminates Charles' law because, again, there's no volumes mentioned. So this is really that Gay-Lussac's law. Once again here, we will do our normal into Kelvin. We go here by adding 273 for our temperatures. And we're going to go 273 plus an 18 in this case, 291 Kelvin. And an 85 plus a 273, 358 Kelvin. Here we are actually solving for, if I put some numbers on them, P2. So kind of like the last one, we're just going to kind of move this guy to the opposite location there up on top. It's going to give us a P1, T2, T1 is equal to P2. Popping in our numbers here, 1.20 up on top. We do need T2 up on top in Kelvin, 358 divided by T1, 291 Kelvin. Kelvins will cancel, in this case, leaving us atmospheres up on top, which is good since we're looking for a pressure. And here we go. Looks like a 1.48 atmospheres, if I am not mistaken. Here we see the temperature increase, and we should expect the pressure to increase as well. And it does look like it did. Any questions on that particular one there? Yeah, I would say most commonly on these two, Charles' law, Gay-Lussac's law is, again, leaving the temperature in Celsius is a very common error that people do most of the time. Talk about another gas law here. That's our friend Avogadro. He had a number, but why not a gas law as well? Seems like a nice thing. So Avogadro's law, again, when we think about Avogadro, we think like 1 mole of something equals 6.022 times 10 to the 23. So again, not surprisingly enough, Avogadro's law involves moles. And it is V1 over N1 is equal to V2 over N2. This is actually at a couple conditions. It's actually at constant pressure and temperature. So at constant pressure and temperature is basically Avogadro's relationship. And one of the sort of interesting things about Avogadro's law, besides the fact it's like any other gas law that you could kind of plug and chug into the equation, is You could also use it in stoichiometry problems if you're dealing with gases and you're at constant pressure and temperature. And what we see is, as you can see, pretty much the mole to mole relationship here, 3 moles to 1 mole to 2 moles, that pretty much matches the volume to volume relationship, which is 3 volumes, 1 volume, or 2 volumes. So sort of a practical aspect of sort of Avogadro's law is if you actually come across sort of a stoichiometry situation where you would normally perhaps have to use a gas law to solve it, if it is at constant pressure and temperature, you could actually do almost like a mole to mole relationship, but just use a volume to volume relationship. So what do I mean by that? If we look at this equation, for example, because it's at constant temperature and pressure, and that's the important part of this. Obviously, if it is not at constant temperature and pressure, you can't use this relationship. But if it is, you could use basically Avogadro's relationship. And if we normally went through this equation, we would say something like 4 moles of NH3 gives us 5 moles of O2. What we could do, because it's at constant pressure and temperature, is go something like 4 liters of NH3 will give me 5 liters of O2. We could also do something like 4 liters of NH3 would give me 4 liters of NO. 4 liters of NH3 will give me 6 liters of H2O. So because the moles and the volumes are sort of related to each other here in these constant pressure and temperature relationships, you could actually do this stoichiometry problem without having to actually go into a gas law like we'll talk about shortly in this chapter. So for example here, they want to know how many volumes of NO are required to obtain 1 volume of NH3. So if we have 1 volume of NH3, basically say we have 1 liter of NH3, and we want to know how many NOs we would have. And we could use the relationship from the equation, which is right here. And we would do it just like we would do stoichiometry with the mole to mole relationship, but we would just do a volume to volume relationship here. And we would say for every 4 liters of NH3, we get 4 liters of NO. And that is just like how we get our mole to mole relationship. It is just the coefficient from the balanced equation. And again, we could do this because of Avogadro's relationship and his constant temperature and pressure. That would tell us, I think I could do the math there. I'm going to try 1 liter of NO would be produced in this case. Now, if I want to know how much water I would get, I could do 1 liter of NH3 and do the volume to volume relationship between NH3 and water, which is for every 4 liters of NH3, I get 6 liters of water. The liters of NH3 will cancel. And basically, we're taking 6 divided by 4 gets me 1.5 liters of water would be produced. So this is sort of a shortcut that you could do if you're under those conditions of constant temperature and pressure and you need to do a stoichiometry problem. It will allow you not to have to use something like we'll see later on, the ideal gas law. But you could still use the ideal gas law, but this is sort of a shortcut calculation that you could use because of Avogadro's sort of relationship. Any questions on that there? Now, if we take some of the relationships that we saw, again, Boyle's law, increasing or decreasing the volume of gas will cause pressure to either increase or decrease. Again, smaller volume, more collisions, more pressure. Larger volume, again, less collisions, lower the pressure. Our heating here in Charles' law, as the lower temperature, the volume will decrease to keep that pressure constant. Higher temperature, it's going to increase to give everybody a little bit more room. And obviously our sort of Gay-Lussac's law, lower temperature, lower pressure, and higher temperature, higher pressure in a rigid container where the volume will not move, basically locked into place in all 3 places. Now, obviously, our Avogadro's law, which is basically the dependency of volume on the amount of gas at constant temperature pressure. Again, we sort of see that relationship of moles to volume relationship. And if we put all these guys together, if we kind of combine all of our gas laws and sort of the relationships together, we do get the, granddaddy of them all there, which is the ideal gas law, PV equals nRT. So PV equals nRT is the ideal gas law. What makes something an ideal gas is we'll talk about also a little bit later on as well in this chapter, but essentially, there's really two things that make something an ideal gas, and that's what we consider most gases, sort of how their behavior is under normal temperatures and pressures of everyday temperatures and pressures. But basically, one thing that makes, again, something a ideal gas is the gas molecule itself. Its volume is much smaller than the volume the container is flying around in. So we assume that the gas, its volume itself is negligible. The other sort of main thing that makes something an ideal gas is the idea that if you have multiple gases in the same container, they basically will not have any interaction with each other. So there's no attractive forces between gases in that same container. There's no repulsion forces between gases in the same container. Hence the ideal situation. Nobody's interacting with each other. And that's what allows us in certain cases, in certain type of calculations, as we'll see in this chapter, to, even though there's multiple gases in the same container, we could almost do the calculation like that gas was in the container by itself. And then you can do a calculation for the other gas, like it's in there by itself, as there's no sort of interaction between them. And under normal pressures and temperatures, most gases will behave like this pretty much ideally and won't have those sort of interactions. We'll talk about at the end of this chapter gases that do interact with each other, and you do have to take those things into account. Those are what are referred to as real gases, unlike these fake gases here that are ideal. Now, when we use the ideal gas law, it's different than all the gas laws we've seen up to this point. It is a one and done situation. There's no two pressures, there's no two volumes, no two temperatures. It's basically one of everything. It is also the most restrictive in terms of units. When you use the ideal gas law, the unit of pressure has to be in atmospheres. When you use volume in the ideal gas law, the unit has to be in liters. Moles should be moles unless you're doing something really bad and wrong. And temperature, no surprise here, does need to be in Kelvin. And really the reason why all these guys have to be in those particular units is because what R is. R is the gas constant. And the gas constant that we use for the ideal gas law is basically 0.08206. And the units are liters times atmospheres up on top, Kelvin times mole on the bottom. So basically it has all of these units in it. So for everything to properly cancel out with the gas constant, everybody else has to be in those units for sure. Now, some people in some books nowadays will round to 0.0821. That's all good. If you want to use that number, it's okay. I personally use the top number because that's what they beat in my head and I can't get it out as much as I try. So that's the one I always use. But a lot of books and stuff will kind of use a little bit of a rounded version of that number. Any questions on that there? Now, some important relationships that we actually see when we talk about the ideal gas law, or just in general, is let's start with STP. STP stands for standard temperature and pressure. Now, when a problem or somebody says, hey, what is the volume at STP or something of that nature, they're actually giving you a temperature value and a pressure value, although they will never usually put it in the actual problem. They'll just say STP. So it is assumed that you know when somebody says STP, that means the temperature basically is 273 Kelvin and the pressure is 1 atmosphere. So those are basically the STP conditions. So if you needed to, for example, go into the ideal gas law under STP conditions, those would be the values that you would use for pressure or temperature. Yes, sir. Yeah, it's your call. Again, I'm good with just the 273, but technically speaking, the right number is 273.15. Not usually, which is why most people kind of round it off anyways, because it usually get rounded off anyways along the way. So if you want to use it, you're more than welcome to do so. And that really is truly the true number there, the one like Kelvin found there. which is 273.15, but most people do round it. But you can still use it if you like to, yeah. Also, by the way, if you're using some other gas law other than the ideal gas law, you could also use 760 millimeters mercury or 760 torr as the pressure if you're doing, not an ideal gas law where it has to be in atmospheres. So you could use that for STP conditions as well. Now, there is a really nice relationship that if you find yourself at STP conditions, you could use this sort of conversion. And if you are at STP conditions, 1 mole of any gas will pretty much equal 22.414 liters. So why would you maybe want to use that? Well, if you happen to be at STP conditions, you could pretty much in a lot of calculations just bypass using the ideal gas law, and you could kind of just use that as a conversion factor. But it is really important to remember that the only time that you should ever attempt to use this relationship is if you're at STP conditions. So if the temperature is 273 and the pressure is 1, you're good to go and you could use that. If it is not 273 or if it's not 1 atmosphere, you should never use that relationship. You should always use PV equals nRT in that situation, yeah. If you don't even want to worry about that relationship, don't worry about that relationship. Just use PV equals nRT in every situation. You could use the ideal gas law in STP conditions. You could use the ideal gas law in non-STP conditions. You could just put the numbers in there and you don't even have to worry about that sort of relationship or worry if you're going to maybe use it wrong or in the wrong situation. So if you remember it and it is the right situation, that sometimes can kind of save you a little time without having to use ideal gas law. But if you don't want to worry about it, always you could go into the ideal gas law. The ideal gas laws we'll talk about towards the end of the chapter when we talk about those real gases is really like a universal gas law. It's like good for like any conditions, any type of situation. That's why we use it and we assume ideal gas situations a lot of times. So we can use this very simplified version of this equation. As we will later see in this chapter, when it's not ideal conditions, that equation becomes very scary looking. There's a lot more things added to it. So let's take a look at one here. Calculate the pressure in atmospheres. If you got 1.82 moles of SF6 gas and it has a volume of 5.43 liters and 69.5 degrees Celsius. Let's see what you come up with. Okay, so once again, we're going to pull out the information here. We do have we are looking for a pressure actually. We do have moles, which is N, 1.82. We do have a volume that's 5.3 liters, and we do have a temperature that's 69.5 degrees Celsius. So just pulling out the information, you can see that really none of the other gas laws really would work except for our ideal gas law, as we only have one pressure, volume, and so forth. Also, a reminder that this is a number that everybody assumes you always have, which is the gas constant. It is very rarely, if ever, even mentioned in a problem. So they usually don't even mention R. They just assume that you have it available to you. So if we look at it, really, we have everything we need here except for the pressure. We just want to always be careful when we use the ideal gas law to make sure unit-wise we're all good. Our moles are in moles, so that's good. I will say also it's very common that you have grams and you need to convert to moles. So molar mass conversion, going from grams to moles, is a very common one. Our volumes in liters, in addition to the molar mass conversion, the milliliters to liters conversion is used a lot here, as we usually will collect sort of the volume in milliliters and has to convert it to liters when we use the gas law. So like normal here, we're going to convert our temperature here to Kelvin. That's going to be a 69.5 plus a 273. It's going to be a 342.5 Kelvin. Solving for P, we're basically just going to send V to the other side and divide it. That will equal nRT divided by V. Putting in our numbers here, we got 1.82 moles. We got our gas constant here with all those units. And we have our temperature of 342.5 Kelvin, all divided by our volume of 5.43 liters. The moles will cancel, the Kelvin will cancel, liters will cancel. That is going to leave us only atmospheres left over, which is good since we are looking for a pressure here. We're going to go to like a 182 times a 0.08206 times a 342.5. Hit equals divided by a 5.43. That's going to give us a pressure here of 9.42 atmospheres in this case. Any questions on that calculation there? It's about 9 times higher pressure than standard pressure, right? So there's a lot of pressure going on. All right, let's take a look at another one then. If there's no questions, what is the volume in liters occupied by 49.8 grams of HCl, hydrogen 1.008, and chlorine 3545 there? All right, see what you come up with here. Okay, so let's take a look again. We're looking for a volume here. We have the mass here of HCl. From that, we can definitely get moles. So basically, we have N as well. We have STP, which is standard temperature and pressure, which does count for actual numbers, 273 Kelvin, and the pressure would be 1 atmosphere. And obviously here we always have R, which is 0.08206. So we can definitely use PV equals nRT. It looks like in this case, it is the grams here that we need to do a conversion to get to moles. So we'll take our 49.8 grams of HCl. We'll use the molar mass from the periodic table. We're basically just going to add these guys. So that's like 3646, I think. 3646 grams per mole of HCl. And that will get us here 49.8 divided by 3646, 1.366 moles of HCl. At this point, we could go into our ideal gas law here. We're going to divide the pressure to the other side, and that will give us V is equal to nRT divided by P. Putting in our numbers, 1.366 moles are 0.08206 liters atmosphere Kelvin mole. 273 for our temperature, and obviously our pressure here is going to be our 1 atmosphere on the bottom. Atmospheres cancel, Kelvin cancel, moles cancel, leaves us liters as our unit at the end. And that will be 1.366 times 0.08206 times a 273. It's going to give us a 30.6 liters of HCl. First off, any questions on that calculation? Any question? No? Okay. Now, could we have solved this another way? And the answer is, yeah, we could have, because we are at STP conditions. So this would have been one of those times where you could use that relationship that at STP, 1 mole of any gas will equal 22.414 liters, which means you could essentially have grabbed your moles right about there before you went into the ideal gas law. And you could have just used that as a conversion factor. And you would do 1 mole on the bottom, 22.414 up on top. Moles will cancel. And lo and behold, we should hit the pretty much same number. Maybe slightly different if we did a little bit of different rounding, but 30.6 liters here in this case. So this is what I was talking about before. You could basically bypass the ideal gas law and use this conversion if you are at STP conditions. But as you could also see, if you went the other way with the arrow, you could also go into the ideal gas law and just bypass that conversion. So you could use either one. They both should give you the same thing. Again, ideal gas law, any conditions you could use it. That conversion though on the bottom could only be used at STP conditions. So that is the difference there. Any questions on any of that there? Okay. So we talked about some gas laws. Let's talk about one where, heck, let's just do everything together. Pressure, volume, and temperature. So because the ideal gas law has that constant in it. If you rearrange the ideal gas law for two different sets of conditions and set them equal to R, because those are both the same numbers, you then can set those guys equal to each other, and we get this gas law here. And in a lot of cases, though, in terms of problems, the number of moles of gases actually remain constant. So this guy kind of reduces down in a lot of cases to this one. And this is what is usually referred to as the combined gas law, because frankly, it combines everybody and all the sort of variables in this case. So that's P1 V1 over T1 equals P2 V2 over T2. Pressure here doesn't matter as long, again, they're the same on both sides. Same deal with the volume, needs to be the same on both sides. Like any other gas law, our temperature here does need to be in Kelvin. Now, the combined gas law, either that version of the combined gas law, or if you want to remember the combined gas law that really comes from the ideal gas law that has the moles in it, if you have to dedicate your time to remembering an equation for your gas laws, I would invest your time in this equation. And if you want, you can invest it in the one that has the moles in it. Why would I invest my time into this equation versus all the other individual equations that we talked about? Because if you know this equation and you come across a problem where they do not mention anything about temperature or moles, or they tell you it's constant, all you have to do is come to this equation and just cross those things out. And now you are staring at Boyle's law, basically, right? If you take this equation here, the combined gas law, and you come across a problem where they do not mention anything about pressures or moles, or they tell you it's constant, you just come over here and scratch that stuff out. There's our friend Charles' law sitting there. If you come across this equation here, and again, you come across a problem where perhaps they tell you that either the volume and the moles are constant, or they don't mention anything about volume or moles, you basically come over here and scratch these guys out. And there is Gay-Lussac's law. You take this equation here, and you come across a problem where they do not mention anything about pressure or temperature. You come over here to this equation and you scratch out pressure, you scratch out temperature on both sides, and there's our friend Avogadro's law. So really, if you don't want to remember all the individual gas laws, heck, just remember this gas law. And frankly, just scratch out whatever is not given to you in the problem, whatever is held constant, and you'll be left with pretty much the right gas law that you need. So I would dedicate my time to this one, and for good measure, just in case you can't remember it off of that one, the ideal gas law. Pretty much if you know these two, you're in business for any problem that you come across. Again, using the bottom one there, just scratch out what's constant, what's not given to you, and you'll pretty much be left with the correct gas law to use. Any questions on how to do that there? All right. So let's try one here where maybe we're going to actually use that law. We're going to consider a sample of oxygen gas at 27 degrees Celsius with a volume of 9.55 liters and a pressure of 2.97 atmospheres. The pressure is changed to 8.25 atmospheres and is heated to 125 degrees Celsius. What is our new volume at this point? So see what you come up with on this one here. Okay, so again, looking at this one, we'll pull out the information. We got a temperature there of 27 degrees Celsius, corresponding volume 9.55 liters, and a pressure of 2.97 atmospheres. We're going to change the pressure there to 8.25 atmospheres. Temperature is going to go up to 125 degrees Celsius, and we are looking for a volume. Now, clearly, the only gas law that we've really seen that has all three of these guys in it is the combined gas law. So it should point you really in this direction. Again, we just want to watch units here and make sure everybody's in the right units. So atmospheres and atmospheres, they're in the same units, so we're good to go. Like normal here, we'll do our conversion to Kelvin. And that's going to give us a 300 Kelvin and a 398 Kelvin there. So in this case, we do have P1 V1 over T1 equals P2 V2 over T2. We are looking for V2, which is right here. That means our other two guys on the right-hand side need to go to the opposite side of the equation there. Wherever my problem went, where did my problem go? There it is. So the T2, which is on the bottom, will go to the top on the left, and the P2, which is on top, will end up on the bottom. Again, opposite location as you go across the equal sign. That will get me a P1 V1 T2 up on top, a T1 on the bottom, and a P2 on the bottom will equal my V2 as those guys go to opposite locations. Popping my numbers in here, we got P1, so 2.97 atmospheres, V1, 9.55 liters, T2, 398 up on top, T1, 300, and lastly, P2, 8.25 atmospheres. So again, Kelvin will cancel, atmospheres will cancel, going to leave us liters as our units. And if we do that there, 2.97 times 9.55 times a 398 divided by a 300 and divided by an 8.25er. That's going to give us a volume here of 4.56 liters. Any questions on that one there? I will say probably this one gives people the most difficulty in the rearranging part of it. So again, if you have issues on rearranging the formulas, just again, remember opposite locations as things move across the equal sign, and that sometimes could help you out. Any questions on that one there? All right, then let's talk a little bit about some other calculations that maybe you haven't done before, which is calculating the density of a gas and also the molar mass of a gas. So as we talked about earlier on in this chapter, when we talk about density for gases, they typically will have units of grams per liter is typically the units that you will end up with when you do the density. And for molar mass, it is typically grams per moles is basically the units that you will end up with. So there is sort of this shortcut formula that you could use. And I'm going to show you in a second, but it basically is based off of the ideal gas law, both of these sort of formulas. But if you want to remember these formulas, you can, but that's just another formula to remember. But it really is sort of based off of the ideal gas law. So the density is mass over volume. So if you want to calculate the density of a gas, you would take the pressure in atmospheres. That right there is the molar mass. That is our gas constant. And that is our temperature in Kelvin. So if you have that information, you can basically solve for the density of a gas by just plugging it in. Now, if you want the molar mass, which you'll end up in grams per mole, you could take the density of a gas. Again, the density needs to be in grams per liter. That's our gas constant. That is our temperature in Kelvin, and that's our pressure in atmospheres. So dRT over P. Now, again, both of these really are just based off of PV equals nRT. And sometimes it's just easier to remember one gas law and sort of think of it as a dimensional analysis sort of problem and get rid of units that you don't want and keep the units that you do. So what I mean by that, let's take a look at this particular one here and see how we could kind of approach it. If we have a 2.1 liter vessel that contains 4.65 grams of a gas at 1 atmosphere and 27 degrees, we're looking for the molar mass of the gas. So the first thing we want to think about is the units of molar mass, which is grams per mole. And we really want to think, do we have any of that information given to us? And hopefully you could see that information right there, right? So obviously here, they gave us the grams part. That means really for this problem here to solve it, we really just need moles. So what is the other pieces of information that they gave us in this problem? They gave us a volume that is 2.1 liters. They gave us a pressure that is 1 atmosphere. They gave us a temperature that's 27 degrees Celsius. And we always have R, which is 0.08206 liters atmosphere Kelvin mole. So if you think about, like I said before, really these are all based off of the ideal gas law, PV equals nRT. We have pressure, volume, temperature, and R. We could definitely solve for N, which is moles, which frankly is the bottom part that we would need basically to calculate the molar mass. So if we take N, it will equal PV divided by RT as we take these guys and divide it to the other side. And we need to make sure, because this is, again, the ideal gas law, we need to make sure everybody's in the proper units. So here our volume actually is in the proper units, is in liters. Our pressure is actually in atmosphere, so it's good. Not surprisingly here, we do need to do our temperature conversion. So we'll add a 273 there, and that's going to give us a 300 Kelvin. So now we could actually put into here everything we need to figure out the moles of this gas. We'll do our 1 atmosphere. We'll do our volume of 2.10 liters. We'll divide it by R, 0.08206 liters atmosphere Kelvin mole, and our temperature of 300 Kelvin. Here, the liters will cancel, the atmospheres will cancel, the Kelvin will cancel. Once again, going to leave us moles, which again is good. So that's going to be 1 times 2.1 divided by 0.08206 and divided by 300. It's going to give us, in terms of moles here, 0.0853 moles. And in this case, that is, again, the bottom part that we need to figure out the molar mass. So now we could get the molar mass of this guy by taking the grams that was given to us in the problem. And by the way, usually that's given to you a lot of times in these type of problems, just the grams. We'll take the moles we just calculated there. And now we have molar mass. So 4.65 divided by our answer, going to give us a 54.51 units of grams per 1 mole will be our molar mass in this particular case. Any questions on that there? So again, you obviously could, if you wanted to, just plugged and chugged into the bottom equation there, figured out the density, or you could just think of it as really a ideal gas law and just try to get everybody into the right units. Any questions on that one there? All right, then why don't you try the density one here I wrote. What is the density in grams per liter of oxygen gas at 778, I think? We'll go with 778 on that, why not? 778 torr and 27.5 degrees Celsius. Okay, so sister again, man, let me take, let's take a look at this. So again, like I said before, if you want to memorize those equations, you could pop obviously into that equation there and solve for density. Again, what's to say you can't remember it or you forgot it or you're not sure. Again, you could use the ideal gas law to help you figure this out. So we're obviously looking for grams per liter. If I take the ideal gas law here, PV equals nRT, and the reason I would perhaps take the ideal gas law is clearly I have a pressure given to me, which is 778 torr. I also have a temperature given to me, which is 27.5 degrees Celsius. And again, I always have R available to me. So if I just look at the ideal gas law and sort of figure out what I have, I do have temperature, I do have R, and I do have pressure. I do not have moles or volume. And I can actually rearrange the ideal gas law and solve for N divided by V. And when I do that, I'm going to divide this guy to that side. These two guys are coming back the other way. And that will give me P over RT. Now, N is moles, right? V is what unit in this gas law? Liters. Moles per liter is the molarity. Yeah, so it's basically the molarity of it. And if we do solve for N over V, That's basically moles per liter, which then if I need to get to grams per liter, that is my molar mass, right? That's going to allow me basically to do that. That is essentially, as you can see, if you look back at the density equation, there is my PRT part of it, right? It's basically, again, based off of the ideal gas law, and that's how they derive that formula. You times it by the molar mass you're in business. So again, both of these sort of calculations really just sort of based off of the ideal gas law. So if I do this, it's still the ideal gas law, which means I still need to make sure everybody's in the right units. So I do have to do a conversion here of my pressure, 778 torr, we need to divide by 760. And that will turn us into atmospheres here, which is what we need for the ideal gas law. And we'll take 778 divided by 760, call it 1.024 atmospheres. Temperature, we'll add our 273 to convert that into Kelvin. And that's going to be 300.5 Kelvin. Now we can put into here our N over V is our pressure, which is 1.024 atmospheres, divided by our R, 0.08206 liters atmosphere Kelvin mole, and our temperature of 300.5 Kelvin. Atmospheres will cancel, Kelvin will cancel. We have liters over moles on the bottom, so when we divide that, it flips, and that gives us moles over liters in the correct orientation when we do the math. So we'll take 1.024 divided by 0.08206 and divided by 300.5, and that's going to give us basically 0.04153. The units here are going to be molarity, basically moles per liter. Any questions on that so far? Again, like I said, at this point, we could go to the periodic table and use the molar mass of O2, which should be 32, 2 times 16, right? Grams per mole. Going to give us 32 grams per mole. So we're going to multiply this here by 32 grams per mole of O2. The moles will cancel, and that's going to leave us grams per liter, which is the density we're looking for. And we'll call it like a 1.33 grams per liter in this particular case. So as you can see, again, that sort of formula that we saw on the previous page really is just based off the ideal gas law. And if you kind of use the ideal gas law and kind of like dimensional analysis and get rid of the units you don't need, keep the ones you do need, it might be easier just remembering a couple more formulas that you really don't need to remember if you kind of use the ideal gas law. Any questions on that there? All right, we laid up there for today.